This is the Chem 1 lecture over net ionics. And the idea of a net ionic equation is that we are going to be writing a complete balanced equation with the states of matter. Anything that is aqueous, we are going to dissolve in step B. We're going to cancel out things that did not change, and then we will finish with a net ionic equation. And all that means is it is the real chemical change that happened. So in this video, we're going to work through 4 examples, and feel free to pause the video along the way. In our first example, we're going to do a double replacement reaction that produces a precipitate. So first, I would start by predicting the reaction. We have strontium chloride reacting with sodium sulfate. And so remember, in a double replacement reaction, we simply just switch the 2 metals. And so our products will be strontium sulfate. So strontium goes right where sodium is, and then sodium pops over, and sodium chloride. And then from here, we're going to take all of these words and we're going to write for step A complete balanced chemical equation. So for this first example, I'll take it kind of slow. So for the compound strontium chloride, we're going to need to get strontium, which I call this my rough draft. Up here has a +2 charge. Chloride is Cl with a -1 charge. And so anytime you're writing a compound with charges, we need our charges to equal 0. So I'm going to need 2 chlorines to balance that strontium. So my first compound formula is SrCl2, plus our next compound is sodium sulfate. So we need to remember that sodium is Na, and looking at the periodic table, it has a +1 charge. And then sulfate is a polyatomic. So if you look it up on the back of your periodic table, it's SO4 with a -2 charge. And so in order to get my charges to cancel, I'm going to need 2 sodiums in my formula. So I'm going to write Na2SO4, and then I will do my reaction arrow. So these are my 2 reactants, and now I need to write my 2 products. This a lot of times goes a little bit faster because you can already see your ions in the rough draft. So we've got strontium sulfate. So with Sr +2 and SO4 -2, those charges cancel, and we get SrSO4. And our last compound, sodium chloride, would be NaCl. And then you want to make sure the reaction is balanced. So I'm going to put a 2 in front of that NaCl. And I think that's it. Now everything else is balanced. And then the last piece of step A, so step A kind of has the most amount of work, is that for each compound, we're going to write its state of matter or its phase notation. So I'm going to start with strontium chloride, focus on the back part, go to the back of my periodic table, look up the solubility of chlorides with strontium. It's not listed on that first line, so you can assume it's a positive ion. It is soluble. So strontium chloride, we would put the state of matter we predict strontium chloride to be is aqueous. So I'm going to put AQ, if I can get my pen to work, under here. And now we're going to go to the next compound and look up the solubility of sulfates. And my positive ion is sodium. So I find my list, I find sulfates. Na is not listed on that top line, so we go to the second line. It is also soluble, which simply means that this compound can dissolve in water. And then go to the next compound, strontium sulfate. And I get sulfates. Oh, we're already there. And this time, strontium is listed, and that is not soluble. So that means this compound will not dissolve in water. And so our expected state of matter is not going to be aqueous, it's going to be a solid. And so that's going to be the exciting part of this reaction, is we're going to see a solid form in our reaction beaker. And then our last compound, sodium chloride, look up the solubility of chloride. So that's that whole group. Sodium's not listed out, and so it is soluble. So NaCl will be aqueous. All right, so this is everything needed in step a complete balanced molecular equation, seeing the states of matter. What we're gonna do from here is start to try to visualize what this reaction actually looks like in a lab setting. So for step B, anything that you labeled aqueous in step A is going to dissolve in water. And when compounds dissolve in water, they split back into their positive ions and their negative ions. So strontium chloride, when we dissolve this in water, we're going to see 1 strontium ion, and we're going to see 2 chlorine ions. So notice that little 2 from A becomes a big 2, because literally when strontium chloride dissolves in water, you're going to see 1 strontium ion and 2 chlorine ions. And if we were to just draw this in a beaker, you actually wouldn't see any of that. You would just see a dissolved clear solution. But then if we zoomed in at that atomic level, we could see the strontium ions and the chlorine ions floating around separately. The nice thing about step B is whatever state of matter you had in A just carries down. So when strontium chloride dissolves, both pieces are still aqueous. You just carry that state of matter down. So step B, I often call the breakup phase. Anything that's aqueous, we are going to break up that compound, which is what it does in water. So sodium sulfate, when that compound dissolves in water, I'm going to have 2 sodium ions, and I'm going to have 1 SO4 negative 2, 1 sulfate ion. So the important part is that when things dissolve in water, you need to be writing your charges reappear. Okay, so I have my reactants, and I'll do my arrow. And now on the product side, I am not going to split up the solid. I'm just going to rewrite it. So anytime you have a solid, liquid, or gas, that just stays together. And then sodium chloride is going to dissolve in water because it's aqueous. So I'm going to see 2 sodium ions. And I'm also, that 2 distributes, I'm going to see 2 chlorine ions. So let's go back to our beakers, because the point of net ionics is we're trying to visualize what is going on in this chemical reaction. So in our first beaker, we have strontium chloride dissolved in water, so that will just look like a clear solution. And then we have sodium sulfate. It dissolves in water, so that would look like a clear solution, so we wouldn't really see anything with our eyes. So you have 2 clear solutions, or we would call them aqueous solutions. And then when those 2 things mix, we are expecting to see, if we look at our states of matter, a solid at the bottom of our beaker. That's what we call a precipitate. And then we'd also have an aqueous solution present of sodium ions and chlorine ions floating around. But if you're asked to describe what a scientist would see, they would start the reaction by seeing just 2 solutions, 2 aqueous, clear, dissolved solutions, and they would see at the end of the reaction on the products a solid form at the bottom of their beaker, as well as an aqueous solution. And then the last part on step B, it's my favorite part, is we look for things to cross out. So we look for things that have not changed throughout the entire chemical reaction. We call them spectator ions. So for example, before the reaction, we had 2 chlorine ions that were aqueous, and after the reaction, we have 2 chlorine ions that are aqueous. We are going to cross those out. They did not chemically change, so they spectated. They just watched the chemical change. Can you spot another spectator ion? our sodium ions. We had 2 sodium ions aqueous before the reaction, 2 sodium ions aqueous after the reaction. So we are going to cross those out as well. Those are called spectator ions. And so what we do for part C, the net change, is now we just rewrite the parts that we did not cross out in step B. It's the real chemical change. So I'm going to rewrite Sr plus 2 aqueous. So when our strontium ions reacted with our sulfate ions, SO4 negative 2 aqueous, they produced a solid. That was the real chemical change that occurred, or we call it the net change, hence net ionics. In a test setting, to make sure you're wanting to get kind of full points, you have to show those charges on the aqueous ions. So the things that dissolve in water, the charges reappear. I should never see a charge on a solid because it does not break up in water. But things that, once again, things I need to see to net ionic is I need to see the charges where appropriate, and I need to see the states of matter in that net ionic equation. Okay, for these next 3 examples, I'm going to move at a little quicker pace. So example 2, we have a reaction, a single replacement reaction with copper and silver nitrate. Copper is going to try to bump out silver. We'll have to check our activity series. Can copper kick out silver? Yes, it is more reactive. And so that means copper is going into a compound. And so because copper is multivalent, I'm also going to have to predict its charge. So according to our periodic table, we can predict a +2 charge. So copper is going to kick out silver and form copper 2 nitrate. So now I'm going to work on translating all these words into symbols. So I know copper is Cu. I know silver nitrate is AgNO3. And I know that because silver has that predictable +1 charge. It is memorized. I call this the 3-2-1 diagonal. And nitrate is from the back of your periodic table, NO3 -1. And we're going to produce just elemental silver and then copper 2 nitrate. So if I look at my rough draft, +2 -1, we're going to need 2 nitrates to make sure my charges balance within the compound. And then you have to balance the entire chemical reaction. So I'm going to need a 2 in front of the silver nitrate, a 2 in front of the silver. And then the last thing is to put our states of matter in. So when I look at this reaction, I have elements. So there is a periodic table in your chemistry room that has it's color-coded, and anything black are solids. And so in this case, copper is a solid as well as silver. And then the periodic table in your classroom would have things highlighted in red are elements that are gases at room temperature. And then there's 2 elements that are liquids at room temperature, which are bromine and mercury. So I'm going to go ahead and put that copper as an element is a solid, so is silver. And then when I get to my 2 compounds, you have to reference that solubility chart. And so something I've kind of just memorized is that nitrates with anything attached in the front are always soluble. Remember, soluble is aqueous. And so our silver nitrate can dissolve in water. It will be a dissolved solution, and so will our copper 2 nitrate. So then step B is taking anything that is aqueous in step A and splitting it up, dissolving it in water. So copper solid is going to stay copper solid. The silver nitrate is going to split up into 2 Ag+1 ions that are still aqueous. And that 2 distributes. I'm going to have 2 nitrate ions. So when this piece of solid reacts with this solution, we're going to produce 2 Ag solids. And then our copper 2 nitrate solution is going to dissolve. So I'm going to see Cu+2 charge form. And I'm going to see 2 nitrate ions form. So once again, whatever state of matter you write in A, it just carries down. And then the last part of step B is you're looking for spectator ions, things that have not chemically changed. And so I have 2 nitrate ions on both sides of the reaction. So copper did change because it started off as a solid and now it's a dissolved solution. Silver started off in a dissolved solution and is now a solid. So that's why those cannot cancel out. And so that's common of a single replacement reaction. There's usually not as many things to cross out. So then to write our net ionic equation, we're going to write down the things in step B that we did not cancel out. And this is the net change, the true change. So I have copper solid. I've got my 2 Ag plus 1, my silver aqueous ions, and that is it. And then on the product side, I produce 2 solid silver and copper plus 2 ions that are aqueous. So just a reminder, in a net ionic equation, we are looking for all states of matter, and then anything that is aqueous, meaning dissolved in water, we should be seeing those charges. All right, example 3 is a reaction between nitric acid and barium hydroxide. So acids have to start with H. Ic came from 8, which is called nitrate, which is NO3 negative 1. So my formula for nitric acid is HNO3. Barium hydroxide is Ba plus 2. Hydroxide is a polyatomic OH negative 1. So to keep things balanced within my compound, it's BaOH2. This is a trickier double replacement reaction. Remember, the positive ions always switch places. And so barium is going to bond with nitrate to make barium nitrate. And then hydrogen is going to bond with hydroxide. H plus and OH negative is actually just the compound water. And we have asked you from our solubility lesson just to memorize the state of matter for water, as you can assume it is a liquid. So kind of jumping ahead, putting in the states of matter. Before I do that, we do need to make sure this compound is, or this whole chemical reaction is balanced. And so you're going to need 2 waters and 2 nitric acids. You'll then go to your solubility chart and place your states of matter. Nitric acid is soluble. You can assume for this unit all acids are soluble, so they can all dissolve in water. Barium hydroxide, if you go read your solubility chart, hydroxides with barium are soluble. And then barium nitrate is soluble. So we have a completed step A. Step B, we're going to dissolve or break up anything that is aqueous. We do not break up solids, liquids, or gases. So then for step B, I'm going to have 2 hydrogen ions that are aqueous, 2 nitrate ions. Break up barium hydroxide, so I'm going to have 1 Ba plus 2 ion and 2 OH negative 1 aqueous ions. I'm going to break up barium nitrate, Ba plus 2, and 2 nitrates. And I'm just going to bring down my 2 H2Os that are a liquid. Okay, then my favorite part, I'm looking for things that can cross out. I've got 2 nitrate ions that are aqueous on both sides. I also have 2 barium ions aqueous on both sides. So my net ionic equation, the real change is when my hydrogen ions reacted with my hydroxide ions to produce water. Now, technically, because I have a 2 in front of everything, this would actually reduce down just to 1 to 1 to 1. So my hydrogen ions reacted with my hydroxide ions to produce water. This was the net change. All right, last example is a double replacement between sodium chloride and ammonium sulfate. So the 2 things in front always just switch places in a double replacement reaction. So I'm going to be producing sodium sulfate and ammonium chloride. So I went ahead and already wrote a balanced chemical equation with the states of matter. So a balanced molecular equation. And so everything, if you notice, is aqueous. So all of these compounds can dissolve in water. So here's what that would look like if all of our compounds broke up in water. And then if you were to look for spectator ions, we had 2 sodium ions before the reaction, 2 sodium ions after the reaction. Started with 2 chlorine ions, ended with 2 chlorine ions. Started with 2 ammonium ions, ended with 2 ammonium ions. Started with 2 sulfate ions, ended with, not 2 sulfates, but 1 sulfate ion. So everything canceled out. So in this case, there would not be a net ionic. No net ionic. Okay, this completes the net ionic lesson. If you have the note packet in the next page, you have several practice problems to practice this process.